Welcome to a fast summary of Chapter 3. We're going to start talking about direct proofs and proof by contrapositive. So in this section, they start off with some buzzwords that you've probably heard before because you've been in lots of math classes before this. And so axioms are statements of truth that we usually accept, and we usually use axioms to derive other things like theorems, corollaries, and lemmas. So all those things follow from some accepted truths that we start with. Getting into it, so the first thing in this section they tell us about what are trivial proofs and what are vacuous proofs. And so a trivial proof is kind of what it sounds like. So in this particular case, no matter like what I started with for p of x, if q of x is always true, it's fine. So like in this example, if n cubed is positive, then 3 is odd. Well, the conclusion is true no matter what here. So since the conclusion is true, it didn't matter about the truth value of p in this case. So like n cubed is positive. So it's always true. Maybe for another example, let x be any real number. If x is negative, then x squared plus 1 is bigger than 0. It's kind of silly. Like that's actually true for any number that I plug in this case. So they give us a little proof of it. And they tell us that, well, x squared plus 1 is certainly bigger than x squared. And I know that that's bigger than or equal to 0. So that gets us into what are called vacuous proofs. And so a vacuous proof is something where what if the premise was false to begin with? So let me slide this over. Didn't realize it was. So what if the premise is false to begin with? So remember the truth table for P implies Q. If P is false, then it doesn't really matter what the truth value for Q is. And so in that case, this is what a vacuous proof will be. So like for instance, if 3 is even, then n cubed is positive. Kind of silly because the hypothesis started with p, 3 is even. That's false no matter what. So in this case, this would be an example of something that's kind of true vacuously. Another example here, if this quadratic expression x squared minus 2x plus 2 is negative or 0, then x cubed is equal to 8 or bigger than or equal to 8. So like what they did is they factored some things and they showed that this expression is actually always bigger than or equal to 0. In other words, they did a little bit of work to show that this p is false, and so that means the statement is true vacuously. So there might be a couple problems on the homework that are similar to that. Moving on. So we are going to start practicing our own, like writing up a proofs. I think in this section it's more, here's a proof, critique it, kind of what method is it, stuff like that. But direct proofs are maybe our first style that we'll go over in this section. And so how do I prove something like P implies Q? Well, I start with P, and I just use the hypothesis that P provides me with in order to try to work my way to show that Q is true. And so there are some things that we get to take for granted. In other words, there's some hypotheses that you get to use and you don't need to show me anything about it. So what are they? You can use without proof that the negative of every integer is a negative, the sum and difference of two integers is still an integer, and the product of two integers is an integer. Another thing that you get to use for free, and this will be crucial to a lot of the problems that we'll do in this class, a lot of these arguments will sound, or we'll use these facts. If you've got an even integer, you can write it as n equals 2k for some k. That's still an integer. In other words, we're just kind of saying that any even number is divisible by 2, is what this says. And so how do even and odds relate to each other? Well, an odd's one more. So you also get to use, without proof, that any odd integer can be written as 2k plus 1 for some k. And they kind of talk through those a little bit. Again, these are crucial to a lot of the homework problems that we'll do. And just to give you an example, if we look at this result 3.4, if n's an odd integer, then prove that 3n plus 1 is an even integer. If we're going to do this by direct proof, all I'm going to do is use the fact that I know what it means to say that n is an odd integer. I'm going to make this little substitution, n is equal to 2k plus 1 for some integer k, and I'm going to plug that expression for n right here into 3n plus 7. And what we do is we plug that in, combine a bunch of like terms until we can finally show that what we're left with is divisible by 2, which again shows that this thing is even. Some other things to notice that are kind of subtle in this proof. When you start writing your own proofs, remember we're going to write complete sentences all the time. When you read this proof here, sure, everything's a complete sentence, but maybe the trickiest thing, they start this sentence now, here's a whole bunch of math, they end it with a period. Make sure that you do that also. This counts as a sentence. And then at the very end, since we show that this is divisible by 2, that means that this guy is even. So then they go through, we'll talk through What else? Scanning through to see. So they just give us some more examples of what direct proofs sound like, so you can read those. Again, you're just starting with whatever P is, and you're only using that to show me that Q is true. Some other things. There's one more specific result that you get to use without proof, which is good. Okay, it's coming up later. Cool. So the next proof technique that we'll have is maybe to prove something by what's called the contrapositive. And so if I have the statement P implies Q, and that's what I want to prove, sometimes that's really hard to do by direct proof. Sometimes it's not obvious how does P actually imply what Q is, or like the things that I know about P, other characterizations of P, don't really help me to get to Q. So another trick that we can do is we can use the fact that we can try to get a logically equivalent statement to P implies Q. And it turns out one logically equivalent statement is this thing called a contrapositive. What is a contrapositive, in case you don't know? It's the statement not Q implies not P. So if we go down here, how do I know that these are equivalent statements? At the bottom of the page, they kind of prove it to you with the truth table. And so you see that the values for the column P implies Q is the same truth values for the column not P implies not Q. So maybe for an example here, when would you use this? So in this case, if x is an integer and if 5x minus 7 is even, then x is odd. And so if you think about, okay, I could try to do this by a direct proof. And in fact, they kind of try to walk you through doing this by a direct proof in the second paragraph here. They walk you through how. But kind of the main thing is, okay, 5x minus 7 is even. Well, that means that that number is divisible by 2. So I get kind of this, I don't know, you'll see comparatively gross statement 5x minus 7 is equal to 2a, and then I got to solve it for x, and I get a fraction, and then I don't want to do that. Instead, though, what we're saying an easier thing to do is this statement is the same thing as saying that as x is not odd, then 5x minus 7 is not even. And so in other words, if x is even, then this number is odd. So if I can show that, then that's the exact same thing. And so you see that took them 2 lines to do. If x is even, then x is 2a. That is much easier to substitute into this expression. And in fact, when they do, I see that I'm able to rearrange this so that it looks like I'm able to rearrange 5x minus 7 so that at the very end it looks like 2k plus 1, where k is this weird 5a minus 4. All I really care about is that it's 2 times an integer plus 1. That's all I need you to show me. Again, notice, hey, they ended that with a period there because, yes, that is a complete sentence. But then that proves it. So sometimes the contrapositive, one, makes the proof just a little bit slicker, but there are some cases where maybe that's kind of the only way to do it. Maybe we don't know how to show it by a direct proof, unless you're Gauss and you can prove one thing like a million different ways. Anyway, other things we're going to be looking at, and you're going to be asked to do some biconditionals at some point. So remember, if you've got a biconditional, that's signaled by a phrase like if and only if. So remember, that's P implies Q, and I also need to prove that Q implies P. So go both ways there. And this example is kind of nice because they use the contrapositive to prove one of these. Don't get converse mixed up with contrapositive. They mean different things. Contrapositive is not P implies not Q. I'm sorry, I said that wrong. Goodness, let me back up here. The contrapositive is not Q implies not P. So double check me there. Not Q implies not P. What is the converse? The converse is just Q implies P. So they're different things. All right, so this brings me to Theorem 3.12. They call it a theorem. This is something that they prove for you here, and you get to use this. So another thing that you get to use without proof, you do not need to justify it to me, is that if x squared is even, or to say x squared is even is the same thing as saying that x is even. In other words, an integer is even if and only if its square is even. You can use that, again, without proof, and you'll need to throughout the semester on some of your problems. Flying through this thing a little bit more. Other things we're running into are what are called proofs by cases. And so maybe just to give you an example of what it sounds like, if I have this result, 3.15, if n is an integer, oops, let me scoot this over, 3.15, it's on page 79. If n is an integer, then n squared plus 3n plus 5 is an odd integer. I need to show that this quadratic thingy is odd, not just for even n's, not just for odd n's, but for all n's. So the way that I would do that is I would take advantage of the fact that I know how to write even integers one way, and I know how to write odd integers another way, and that'll give me stuff to substitute into this. So what am I saying? We should break this into 2 different cases. What if the integer I start with is even? then I'll show that this thing is odd. That's what they do in case 1. And then I'll go to case 2, which is what if the integer I start with is odd? And then I'll plug this 2y plus 1 or 2k plus 1. I don't know why they don't like k in this example. Anyway, I plug that back into this quadratic up here, and then I whittle it down until I get, oh yeah, it's 2 times an integer plus 1. It's still odd. Great. So sometimes you are required to break things into 2 cases. Let's see, in case you didn't know, integers have the same parity. All that's saying is that they're both even or they're both odd, so like that matches, or they're opposite parity if one is even while the other one's odd, or vice versa. So the other big kind of convenient thing that'll make your life a little bit easier is the concept of without loss of generality. And so they talk about that a little bit in the bottom of page 80 here. And so sometimes maybe I have a proof by cases, but maybe case 1 and case 2, they're really the same thing besides the different letter. So what do I mean by that? Let's look at this theorem to prove here. Let's let a and b be integers, then ab is even if and only if a is even or b is even. Now, if I was to put this into 2 cases, naturally you might think, well, case 1, what if a is even? I'll go through the little proof. It probably works. I mean, they call it a theorem. Then I go to case 2, what if b is even? The idea would not be any different other than the fact that b plays the role of a. We don't need you to write that proof down again. We don't need to read it twice. So what we would say is in the very beginning, we would say, without loss of generality, just pick one of these guys to be even. Because why would we say that? What does that indicate? That indicates to us that the argument you're about to make, it works no matter what. So like it would be the same argument for b is what you're trying to indicate to me. So over here, just another example of like how do you use without loss of generality. Oh yeah, just in case sometimes if you're worried how picky we're going to be. It is fine. It's pretty common to abbreviate without loss of generality. You're welcome to write it out if you want to, but it's more common, I think, to say WLOG. And so if you want to use that in your homework assignments, that's totally fine with me. I won't count that as like a symbol. Okay. And so, and they actually go up here to this theorem 3.17. Let's see, how would this without loss of generality go? So I think this is the same thing we started with a moment ago. So AB is even if and only if A is even or B is even. Again, I don't need 2 cases to do this. It's going to be the same argument for A as it is for B. So let's first assume that one of them, or that A or B is even. So let's assume that. So now is where we'd say, without loss of generality, let's pick one. Let's say A is the even one. Then we'll go through the argument and we'll show that AB is even. And then we're done with that. So that would be it for that direction. Now, if you notice, well, what's the rest of the proof? We've got a biconditional here, so then they have to show me the other way. And so in order to do that, what they're actually going to do is they're going to do the contrapositive of AB is even implies A is even or B is even. So notice they assume that one of these two is odd. So again, they're showing the contrapositive to show kind of this forward direction here. And that's just kind of a stylistic thing because that argument's probably going to be a little bit easier to make than directly showing that if AB is even, then one of these two is even. Those are just things you kind of get a feel for. If you can do it the direct way, that's great. If you can do it by contrapositive, that's great too. Just pick one that works for you, unless the question specifically asks you for a method. I think the last thing in this section is just kind of evaluations of proofs. You want to be able to read through a proof and identify, like, well, what's the strategy that they used in each case. That's really the main thing of that. So far, strategies, again, are something like a direct proof, or is this a vacuous proof, being able to identify that, or is it a trivial proof, or using the contrapositive are our main ones. You've probably all heard of something it's called proof by contradiction. That comes a little bit later on. We'll get to that too. It's another good proof technique that's very useful sometimes. So we did it. That is it for chapter 3.